Okay, so this is a video on what we call trigonometric substitutions. So this is a set of advice. In general, this is a set of advice for when you see things that look like this. And so the common thing that you see here is you see a number a squared and you also see an x squared, and they could be added or subtracted. It could be x squared. It could be like this, x squared minus a squared, or a squared minus x squared, and you do different things in each situation. Anyway, for this one, what we do is we let x equal a sine theta, and one different thing that you're going to notice about this is that this is sort of like reverse substitution. Usually when we talk about substitutions, I'm introducing a new variable that I call w, and I let w be a function of x. In this one, we're introducing a new variable that we call theta, and x is a function of theta. That's how this is a little bit backwards compared to standard substitutions. Anyway, in this situation, this is the substitution we do. Each one comes with some technical information about what interval theta should be in. If you're doing sine, then we want theta to be like the arc sine, so I restrict theta to be the interval where arc sine is. This is a little bit technical information that we often do not think about explicitly, these intervals for theta, but the information is included. We anticipate using a trig identity whenever we do this. And the whole point of letting x equal a sine theta is so we will end up using this trig identity. And then here's this one. This is similar, except if I see a plus in between, then I do x equal a tan theta. There's an interval that theta needs to be in, and I anticipate using a different trig identity. And then here's one for secant. Let's do an example. So here I have an integral to do, and I do see something that looks like these. By the way, usually you have a square root on these. Sometimes you don't, but usually you see a square root on these, and this is no exception. Anyway, this looks like a squared minus x squared. Looks like this one. And a is 3 because this is 9. So I know what to do. Whenever we do a substitution, including a trig substitution, then I need to do something with like the d stuff, like dx. So this would be 3 cosine theta d theta. And then this turns into, okay, x is 3 sine theta, so this is that. Here, I'm not going to try to be clever. I'm just going to literally replace all the x's with 3 sine theta, and the dx gets replaced with 3 cosine theta d theta. Okay. Let's try to simplify. So 27 sine cubed theta over, okay, I don't want to go too fast. So this is 9 minus 9 sine squared theta. Okay. Now let me tell you what's going to happen. This part down here, I'm going to pull out a 9, and then it's going to look like this. So okay, 27 times 3 is 81. So I'm still just sort of simplifying this. I can pull this 9 out. In fact, let me pull it all the way outside of the square root. If I'm pulling a 9 from the inside of a square root, when I pull it outside, I do the square root of it, so it becomes a 3. And then underneath the square root, I just have 1 minus sine squared, and there's my identity. Okay, 81 over 3 is 27. 1 minus sine squared is cosine squared. Now, I've been going pretty slow, but let me do, oh, almost forgot to write my d theta. But like I said, I've been going pretty slow. I probably could have skipped some of these steps and done some of this in my head. But the whole point of this is we want to deal with this square root. And after using the trig identity, I see square root of cosine squared, which is just cosine. In fact, since that's just cosine, why don't I just cancel that whole thing with this cosine? Okay. And I could have pulled this 27 out, or I could have pulled all my numbers out a while ago, but let me finally do it. So I end up with 27 sine cubed theta d theta. All right, luckily we just learned all about how to integrate powers of sine and cosine. So I don't see a cosine here, but we can act like it's cosine to the 0. And for powers of sine and cosine, as we learned, what you look for is an odd power. The invisible cosine is an even power, because that's like cosine to the 0. But the sine does have an odd power. So let's do the thing that we do. I save one that has the odd power. So I'm going to save a sine theta. I like to write that all the way to the right. And then what's missing is a sine squared, but I'm going to replace that using the identity, because instead of sine squared, I'm going to write 1 minus cosine squared. All right, and then what do? We do a standard substitution, so I'm going to use the letter W. W is going to be cosine. That way dW will be, well, dW will have, it will be negative sine, but negatives don't bother us. So this 1 minus W squared, and this is negative dW because dW has this negative there. Okay. Yeah, so I'm just going to run this negative through. This is nothing. Oops. dW, sorry. And then we just integrate it. So this turns into 1/3 W cubed. This turns into W. At this point, I should start writing plus C. I can simplify this a little bit, but let me take a step back and think. I made a couple of substitutions. I made this substitution and then the original trig substitution. I do want to put my final answer in terms of the original variable x. So this is going to take, I'm going to take 2 steps back. I have it in terms of W. I'm going to replace all my W's with cosine thetas, and then I'll have an answer in terms of theta, and then I'll have to figure out how to put my answer in terms of x. Okay. So let me do one of those steps now. I'm going to replace all the W's with cosine theta, and maybe I'll multiply this 27 through. So 27 times 1/3 is 9, and then W cubed turns into cosine cubed theta. And then this 27 distributes, so minus 27, and then W is cosine theta plus C. Okay, so now I have my answer in terms of theta, and the last thing I want to do is get it in terms of x. So for trig substitutions, we do a particular thing here. I have cosines, and x is 3 sine. So what do? I'm going to draw a right triangle. This right triangle is going to have an angle of theta, and I would like to label this right triangle so it represents, it represents the substitution that I did. So if this is the substitution that I did, Sine theta is x over 3, so I solve it for whatever the trig function is. And what is our old friend SOHCAHTOA? Sine is opposite over hypotenuse. So if I want this triangle to represent that, I'm going to put x across from theta, so that's opposite, and 3 on the hypotenuse. I can solve for the last side. You're probably pretty good at this. We use the Pythagorean theorem. It would just be the square root of this squared minus this squared. And here's a running theme for trig substitutions. When you get to this step, when you're drawing your triangle, the missing side that you figure out is usually, if you look back at the very first thing that gave you the idea to do a trig substitution, it's usually the same thing. Square root of 9 minus x squared, square root of 9 minus x squared. Anyway, that's just a thing that happens. So what do we do? Let me sort of draw a bubble around this. We are ready to write our final answer. So I had this, and somehow I need to write this in terms of x now. So I can look at the triangle and figure out cosine theta. Cosine is adjacent over hypotenuse. So here's cosine. And then I cube it because it's cubed. Minus 27 times, well, another cosine, except this one isn't going to get cubed. Plus c. And okay, I said that was the final answer, but let me just clean it up a little bit, because 3 cubed is 27, and I can cancel that with a 9, so I'm going to get 9 minus x squared to the 3 halves, because this is like a 1/2 power, and then I cube it, and it's a 3 halves power. 9, and then a 27 down here leaves a 3 down there. This turns into a 9. Okay, now I'm done, I swear. Okay. So that's how we do trig substitution. Let's do another one. So now we've got this, and this looks more like this one. Of course, instead of x, I have t, but that doesn't bother us. The point is I have t squared minus a number, so it looks like this, which is not really the same as this. So it looks like my a is 4. So I'm going to let t be 4 secant theta. And I should look for a way to use this trig substitution, of course, or this trig identity, I mean. Of course, when I put this there, it's going to turn into a 16 secant squared, and then I'm going to pull a 16 out of the square root, and maybe we see where this is going now. All right. So this... Oh, yeah, before I do anything, I should have done dt. The derivative of secant is secant times tangent. So it's like that. Okay, so dt is that. Over, okay, t squared, that's 16 secant squared theta. And then I've got this, which is 16 secant squared theta minus 16. Whoops, I already have my d theta right there. Okay, so let's simplify this, and really, I mean, there's a couple of things to do, but really my eyes are mostly on this square root part, because this is where the trig identity is going to come in. But let me take care of these other things. So 4 cancels, so I leave a 4 there. Secant cancels, and I'm left with 1 secant on the bottom. And, okay, let me rewrite this. So this stuff is gone. On the top, I've got tan theta d theta. On the bottom, I've got 4. I still have this secant theta. And, okay, I want to pull the 16 out. And once I pull it outside of the square root, it just becomes a 4. And let me try to do this a little bit faster. Once I pull that 16 out, what I've got in there is a secant squared minus 1, which is tan squared. So it's just that. Now that I have it written this way, this is kind of the magic of trig substitution, is we end up with a square root of a perfect square. And in fact, so this is just tangent, and in fact, I can just cross it off with that tangent. So these things tend to simplify a lot once you use the trig identity and all that. All right. Okay, so I've got a 16 on the bottom. Maybe I'll use this opportunity to write that on the outside. What else do we have? I've got a secant on the bottom, which we should remember that secant is the reciprocal of cosine. I would much rather just write cosine than have a secant on the bottom. That's the same thing. So this actually turned into one of the easiest things ever. This is just 1/16 sine theta plus c. Of course, all the calculus part is done, but we want to write our final answer in terms of the original variable, which was t. So now we're going to do the triangle thing again. I'm going to draw a triangle. One of my angles is going to be theta, and I want it to represent this. So secant theta is t over 4. And yeah, secant isn't really part of SOHCAHTOA, but except it's the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant would be the reciprocal of that. In other words, hypotenuse over adjacent. So t goes here, 4 goes here, and guess what goes here? This squared minus this squared. Same thing as that. Okay. And maybe I'll just continue from here because I'm really close to done here. Now that I have this picture, sine is this over this, because sine is opposite over hypotenuse. And that's it.